Hi, my name is Devlina, and today I'll be talking about explainable AI for robot failures, generating explanations that improve human assistance and fault recovery. In present day, robots are increasingly being deployed to work in human environments to accomplish complex tasks. And while these robots are successful in executing these tasks, unexpected failures can be inevitable and may require human assistance for recovery. Yet, in most cases, the co-located users are not AI experts or roboticists, and without additional information from the robot, cannot understand the cause of failures. This leads us to the main objective of our work, generating explanations that can help non-experts understand unexpected failures and assist in failure recovery. Our work relates to prior work across multiple areas. In the first domain of explainable AI, most of the work focuses on understanding the outputs of deep learning models. Traditionally, these models have mainly focused on single classification tasks, and explanations are aimed at AI experts. More closely related to robotics, the subfield of explainable AI planning has focused on explaining sequential decision-making tasks. Most prior work in this area has focused on explaining why one planned solution is more preferable than another. In fault diagnosis literature, a number of techniques have been developed for robot failure recoveries, but these systems are aimed at software developers and expert operators. Finally, recent work in AI has demonstrated that human-centered explanations in the form of natural language can benefit non-experts in understanding the behavior of autonomous video game agents. We build upon the findings of the shown research areas here. Specifically, our work lies at the intersection, and we focus on producing natural language explanations that enable everyday users to understand and correct errors encountered during robot task execution. To accomplish this goal, we answer the following research questions. How should error explanations be defined in the context of a robot task execution? What type of explanation should be provided to help non-expert understanding? And how can these explanations be autonomously generated? To formalize the definition of an error explanation, we build on prior work in the explainable AI planning community. Given some planning problem delta, we assume that our robot has a plan pi consisting of a sequence of actions A1 through N, which transition the robot from some initial state I to the goal state G. We address scenarios in which some action within the plan, denoted by A sub I, failed to complete due to some failure scenario F. We then define an error explanation as a natural language phrase that describes A sub I and F, enabling a user to understand why plan execution stopped. For example, if the user wonders why the robot cannot pick up the coffee canister, then an example explanation would be the robot could not move its arm to the coffee canister because it is occluded. So given these definitions, our first research question is to then identify what information should the robot communicate to the user. We identified several types of information that were readily available to the robot, including the history of past actions, which we denote as A sub t minus 1, the observed action that failed, denoted by A sub t, and other contextual information such as objects in the scene or various internal sensor states of the robot that we denote as C of t. To determine which types of information are most helpful to non-experts, we conducted a user study in which participants were presented with videos of simulated robot errors like the one shown here on the right, as well as with hand-scripted explanations containing various combinations of factors. Our baseline condition had no explanations, and this represents the most common use case in today's robots, which don't have the ability to explain their errors to users. Action-based explanations conveyed only the action that failed. Context-based explanations conveyed both the failed action and the context surrounding the action. And we also included history-based study variants for both action-based and context-based explanations, and this added information about which previous action was successfully completed. For our work, we evaluated three types of failures in the home environment: navigation, arm motion planning, and object detection failures. And for each of these failure types, we considered two different failure causes. We further separated our failures based on their causal groups, where the navigation failures were categorized as internal failures and the rest were categorized as external failures. We define internal failures as failures caused by software or hardware failures, and external errors as failures caused by some condition in the environment. Now, for our study design, we recruited 70 participants from Amazon Mechanical Turk. There were 13 to 15 participants in each study condition, and each participant was tasked to watch a robot encounter a failure scenario and answer questions related to identifying the cause of the failure, as well as providing a solution to the failure for robot recovery. The user study was broken up into 2 stages. In the baseline stage, users saw 6 failure scenarios with no provided explanations, and in the explanation stage, users saw 12 more failure scenarios with explanations provided from their study condition. The intuition for a 2-stage study was to first establish each participant's baseline understanding and then measure the effect an explanation may have on improving their understanding. To measure this improvement, we had 2 metrics, failure identification and solution identification, which measured their abilities to correctly identify a failure as well as identify a solution, and these were calculated by an average F1 score difference between the 2 stages. Using these metrics, we first analyzed how context affected users' failure identification and solution identification, and as we can see here from the graph on the left, the context-based explanation significantly improved the user's ability to identify failures and provide solutions as recovery to robots. Next, we also analyzed how including history of completed actions impacted the user's failure and solution identification, and from the graphs here we see that the history significantly improved their understanding of a failure as well, and also improved their ability to provide a solution. We also examined the impact of each explanation type specifically on external and internal errors. We found that for context-based history explanations worked best across all cases, but were particularly useful for explaining internal errors such as localization errors. For more details on these results, please see our paper. From these results, we see that the best performance is achieved when we communicate history in the form of the previous successful action, the current failed action, and any known context. Our next research question is then, how do we train a computational model to autonomously generate such explanations and generalize to new scenarios? To achieve this goal, we use an encoder-decoder model. On the left, you see the model architecture. X represents the input to the encoders, which are the embeddings of all objects detected near the robot. H is the output of the encoder, and the decoder takes in as input H, as well as N, which is the set of continuous features from the robot state space, and O, which is the embedding of the desired object. The decoder then generates Y, which is a sequence of words that make up the final explanation. To train our model, we collected 72 failure scenarios from Gazebo, 60 of which we used for training our model through a grouped leave one out cross-validation, and the remaining 12 we used for testing. The confusion matrix shows the average performance of our model across 10 folds. As you can see by the true positive rates, our model does a fairly good job in generalizing failure types. However, as seen here by the yellow sections, the model has room to improve, and we suspect that with additional training data, the model can differentiate failure scenarios with even greater accuracy. Now, given our model performance, the ultimate evaluation of the success of our model was in how well the model-generated explanations could help users in failure and solution identification. In the ideal case, we would expect to see performance similar to our hand-scripted context-based history explanations shown here in purple. As you can see, our model-generated results, shown here in teal, very closely match our idealized hand-scripted results and are just as effective in enabling users to both identify the source of failure and the correct solution to the problem. In summary, we showed that natural language explanations are highly effective in increasing user understanding of robot errors. We found that the most effective explanations include both a history of recent actions and a description of the robot's understanding of its environmental context. Finally, we contributed a sequence-to-sequence model to autonomously generate explanations that improved user performance in failure and solution identification. With that, I'd like to thank you all for listening.